Hello, I'm Mike Westcott. I'm the robotics instructor at WSU Tech at Wichita, Kansas, and we're going to talk about robot coordinate frames today. Our learning objective for today is understand and calibrate Fanuc frames and how to use them in your programs. So the different learning objectives, again, we're going to understand 3D coordinate system, planes, origin, right-hand rules, the different frame types, create tool frames, create user frames, create jog frames, how to save frame data, and I'll show an example of using frames within your program. To understand coordinate systems, you need to understand the Cartesian coordinate planes coordinate system. The coordinate system, Cartesian coordinate system is made up of 3 planes: the XY plane, the YZ plane, and the XZ plane. The intersection of these planes all these planes are at right angles to each other, and where they intersect forms a Cartesian coordinate system. The intersection between 2 planes forms an axis. First axis is the x-axis. It's the intersection between the y plane and the xz plane. The y-axis is the intersection between the xy plane and the yz plane. And the z-axis is the intersection between the xz plane and the yz plane. The center of all these axes is the origin. And all the axes combined together makes up a frame. A point in space can be measured from offsets of all these different axes to the distance out there at its location. Your first measurement will be in the x direction. In this case, it's 4 units in the x direction. We don't know the measurement of these units, so we're just going to call it 4 units. It could be inches, could be millimeters, could be something else. In the y direction, it's 3 units. Z direction, it's 6 units to that point in space. So that'd be a XYZ location of 4, 3, 6. You can also describe orientation. So Cartesian coordinate system commonly describes the location, XYZ. You can also describe orientation, which is commonly referred to as the yaw, pitch, and roll, which are rotations around all these axes. In the Fanuc representation, yaw, pitch, and roll are known as WP and R because Y is already used for the Y-axis. Frames, again, are the intersection of all 3 of these axes. Usually when you represent a frame, you only represent the positive parts of the axis. And frames are a point of reference in space. So, for example, if I was looking at an object and we were both in the same room looking at that same object, you'd be standing in a different spot than me looking at that object. So the orientation of that object would be off a little bit from what I'm seeing it. That's commonly referred to as a frame of reference. So the way you see the object and the way I see it's going to be a little bit different because we're standing in 2 different spots. Frames form a point of reference for the robot. Like I said, there's multiple different frames on a robot. We'll talk about those here in a minute. The right-hand rule is a good way to represent a frame using your hands. So you take your right hand and you point your pointer finger out. You point your second finger to the left and your thumb pointing straight up. Okay, so your pointer finger becomes your x-axis, your second finger is your y, and your z is your thumb. To form the rotation around that axis to show positive direction, you just bend those fingers in and curl them around the axis, pointing your thumb in the direction of the positive direction of the axis, like in that representation on the slides. The direction that your fingers point is the positive direction of rotation. You could do the same thing with the X or the Y by pointing your thumb in the positive X or Y direction. There are many different types of frames in robot world, robot language. There's a common standard, the ISO 9787, which gives a description of all the frames, called robotics and robotic devices. And that standard world frame is out in space. It's a common location. And base frame is in the bottom of the robot. tool frame or mechanical interface coordinate system is actually at the flange of the robot, the tool flange. And the tool frame is where the work is being done in the robot. In this case, it's between fingers of a gripper. The task coordinate system is out here on the fixture of the frame, or your tool fixture. The object coordinate system is located on the objects you're working with. You can have multiple object coordinate systems on different objects sitting on the fixture. There is a camera coordinate system that relates any cameras in the system back to the robot, so you can orient based off that camera system. 8 shows the TCP, which is basically your tool frame coordinate system. We'll describe that in more detail later. And obviously, your 9 points to your gripper. There are, in the Fanuc world, 5 different common frames they refer to. One is the world frame, then the tool frame, the user frame, jog frame, and cell frame. We'll get into details of those in the next few slides. All right, so the world frame is in the base of the robot. It is not a changeable frame, so it can't be moved, can't be manipulated in any way. It's located at the height of the J2 axis and centered on J1 axis. So it's not right at the base like it is on some other robots. It's actually floating at the height of the J2 axis. It's commonly referred, or user frame 0 is commonly referred to as your world frame. You can't change it. Okay. If you were to jog your robot in world frame, which is one of the jog methods, you'll see that the, let's look back at the frame real quick here. You got your Z-axis points straight up in positive direction. Your Y-axis is pointing to, we'll call the left side of the robot. If you're standing behind the robot, this would be the left side. And then the X-axis points straight out the front of the robot. So if you're jogging the robot, their X-axis pointing straight out the front, or Z-axis pointing straight up. It's as if you take this frame and translate it out to the tool when you're jogging it. So the tip of the tool, or in this case, the tool flange, there's no tool on it, will be going straight out in the X direction if you jog it in X, straight up in the Z if you jog it in the Z. If you jog it in Y in a linear jog, it's going to come straight at you if you're going negative, and straight away from us if it's going positive. Any rotations will act as if you take this frame again, translate it up to the wrist, rotate around the axis. So if I was to rotate around the X axis, for instance, it would rotate towards me in the positive direction because I'm pointing my thumb out like that with the X. Then put positive rotation is going to rotate around. It would rotate toward me and then away from me in a negative direction. If I was to rotate around Y, this green frame here represents a 45-degree rotation around Y. Let's see, so positive, this would be if I was pointing the thumb out in the Y direction out like that, right, which is pointing into the page because that positive Y is going into the page, then my rotation, forward rotation would be positive. So this would be a positive 45 degrees rotating out. Okay. All right, tool frames. XYZ defines the location of the tool frame origin relative to the faceplate, right? So tool frame is a relative offset from the faceplate. So your default tool frame is at the faceplate. Not any of the tool frames when you first start out, it's going to be that default location, right at the center of the faceplate. If all your axes are at 0, it's going to be just like it's shown. Let's see. So by default, yaw, pitch, and roll define the direction we want the tool frame axis to point relative to the faceplate. So that's when you translate your tool frame. There are default 10 frames in tool frame. There is a variable you can change to add more frames. In R30IB, you have 29. In the R30IB Plus, you can have up to 253 frames. When we translate a tool frame or calibrated tool frame, you're basically doing an offset from the tool flange. So in this case, we have a standard pointer that's just a straight pointer. It's just going to take the tool frame and translate it out to the tip of the tool. No change in orientation. By default, that orientation Like I said, if all axes are at 0, it's just like it's shown with the z-axis pointing straight out from the flange and the x-axis pointing up, which if you use your right hand rule would make the y-axis pointing to the right of the robot standing behind it. There are several different examples of different tools you could put on the end of that robot. With the welding torch here, if you were to take and translate that in a what we call a 3-point method, it's just going to translate your orientation straight down to this point right here. And that point is what we call the TCP, or tool center point. That is the point where the work is done by the robot. In this case, it's welding. In fact, 3 of these cases, it's some form of welding. Typically with a welder, though, you're going to want your z-axis pointing straight out the tip instead of at an off angle going straight down like that. So we're going to want to use a different method known as 6-point method, and we'll learn how to do that later. Or you can use direct entry method if you know the exact size and shape and orientation. Spot gun here, TCP is right in between the electrodes. This other spot gun, again, TCP is right between the electrodes. And again, for either one of these, we have to use a different, other than the standard 3-point method, like 6-point or direct entry, to get these orientation of our tool the way we want it. This is a gripper example, a generic gripper. Your center of your gripping force is going to be your tool center point, right? So in this case, the fingers would come together right underneath the tool flange, and your orientation in this case would not need to change. It'd be a direct translation, so you could use a 3-point method. User frames are a reference for all positional data. So anything in the program that you create is going to reference some form of user frame. It may be the user frame 0, which is the world frame, but it's going to reference from some user frame. The default location is same as the world, so it's right at the base of the robot, or in this at J2 height, center line of J1. But you're going to translate it out to match up with whatever your whatever work you're performing. In this case, we've got these 2 pegboard shapes in the plate here. They're both identical placements and spacings. So you could center up a user frame at the apex of both of them, here and here, and center a x-axis along one side like they're showing here. And if you place this user frame correctly on both sides, then you can reuse your user frame and change your user frame and reuse the motions that you're moving to put the pegs in a hole for one pattern and just run them again over here with a different user frame. And it's what we mean by reuse code in different frame, right? They're user defined. They can be placed at any location, any orientation you want. There's up to 9 default user frames. You can again change a variable to allow it to have up to 61 frames on R30IB and up to 253 frames on R30IB plus. A jog frame is a similar concept to a user frame. Only in jog frame, positional data does not reference a jog frame, which basically means that you cannot reference a jog frame within a program. It's used to help line up with objects, so you can line up a user frame to allow you to be able to jog it along the object better for when you're doing all your different moves when you're creating your program. There are up to 5 different jog frames. You cannot expand them. There's only 5. A cell frame is a common reference frame when you have multiple robots within a cell. So in this example, we show 3 different robots. All of them reference back to a cell frame. In fact, there's even a cell floor origin in this picture that references a cell frame. We will not learn how to use a cell frame in this lesson. Just wanted to refer to it and show you there's that frame. All right, there are multiple jog methods for the robot. There are 5 of them. 4 of them are Cartesian coordinate system frame jog methods. Then joint is not. That's why I have the not symbol on there. You access and move through different jog methods by hitting the coordinate button, and you'll see at the top right corner of your screen, you'll see the description of what jog method you're in. Change as you hit the coordinate button. To select which coordinate frame you're using, or the ones that have multiple selections, you'll hold down the shift button and hit coordinate, and that'll allow you to change the tool frame, jog frame, or user frame in what they call the jog menu. All right, when we go to calibrate tool frames, there are, we'll say, 6 different methods. One of them is mainly used for 4-axis robots with no tilt, the 2-point plus Z method. We will not learn how to use that method in this course. We typically use articulated robots, so we don't have a need for it in this program. There's 3-point methods. That's, again, one that does not do translation or orientation, only does translation. 4-point method, again, does not do orientation, but allows you to correct for error by giving feedback and telling you which point is the most off. So now you have 4 points to calibrate, so you can change one of them without throwing off the rest of them, and you get it closer into the calibration. Give you less error. The 6-point method, again, allows you to change your orientation. There is a 6-point XY and a 6-point XZ method. It allows you to move the robot in either the X and the Y direction or the X and the Z direction to tell it which way the frame is oriented. And then there's the direct entry method, which is used if you know the offset of the TCP by measuring it or AlphaCAD data. Okay, so the tool frame, there's 2 different examples here. One's properly calibrated, one's improperly calibrated. One up in the top right corner here is improperly calibrated. You can see that the tool flange moves in a linear direction when you do a linear move. And then you make an arc motion at the end of the tool here. The properly taught TCP, however, if you have it taught correctly, the tip of the tool will be what moves in a linear direction or linear fashion from point to point. When you're doing a move L or some form of linear jog. All right. When we do a TCP calibration with 3-point method, we're going to teach it 3 different points in space. We'll set up a probe on the table, another probe within the gripper or whatever your tool is. You can even use the welding wire in the welding tip as your probe. And then you'll touch it from 3 different angles. Typically you want greater than 90-degree angles, but less than 360 degrees from all the way around. To access tool frame 3-point method, you'll hit select, then setup, then frames. If you're not in the tool frame menu, when you get there, you'll have to hit other and then select tool frame. You'll modify the first existing available frame. Typically, you'll look for one that's all zeros, and you'll say EOAT over in a tool, EOAT and a number. In this case, I pulled up an example that had names in it, but they look unused because they're all zeros. Modify it will. You just select that one and you'll hit enter, and then the detail, or enter or the detail button to access it. Once you're inside it, you'll hit the method and then select the 3-point method. And it should show the menu looking like this. Obviously, you want to use a comment to tell it what kind of frame it or what kind of calibration you're doing. So if you were using it for a welder, you'd say welder. If you're using it for a gripper, you put a gripper, maybe even more description by telling it what brand of gripper or something like that. You're going to calibrate 3 different approach points in this method. So you'll move your cursor down to approach point 1, line up your first direction with the two points touching each other, and press shift plus F5 to record. And then you just repeat. You'll go to the next point, record at point 2, repeat again at point 3. Once all 3 are calibrated, it'll show new position calculated, and the X, Y, or Z values will update. Yaw, pitch, and roll, WPNR will not, because this is a 3-point method. It does not change that orientation. To test any of the tool frames, you're going to change the jog method and the tool frame number in your jog menu. So again, you'll hit shift plus coordinate to access the jog menu. Then you'll type in the tool number you want, and then you'll hit the coordinate button by itself to access the tool jog method. And then you'll use these X, Y, and Z with the arc neuron over the top of them. Those are your yaw, pitch, and roll buttons to jog it. Obviously, you got to hold the dead man and the shift key to be able to jog it. This is going to jog around your minor axes, allowing the tip to stay touching. So your probe and your tip will stay touching, and you'll notice that you'll rotate around a point in space. If you rotate or instead jog with the linear jogs, you'll see the tip moving, especially if you do like the Z direction. You'll see the, if you say it, do the Z minus, that probe will move back this direction. Z plus will move this direction. Right, and then X and Y would match whatever your tool flange X and Y were. All right, so the next method is the 4-point method. In the 4-point method, we get feedback provided to tell how well the points are taught. We use the feedback to tell what points need retaught. This was released in the R30IB 8.3 update. So any robots older than that will not have this calibration method. Obviously, it's the same method to get into it as there was in the using the 3-point method. You'll just select 4-point instead. So you got to go through the menu setup button or setup and frames off of the menu screen, then other, and then tool frame method, and select 4-point method. Again, you'll want to rename it with a comment to match whatever tool you're trying to calibrate. And it's the same basic method as using the 3-point method, where you shift plus record to record your points. Once you get them all recorded, you'll see a mean error and a max error. The mean error represents your total error between all 4 points. The max error is a deviation from the worst point from the furthest point. And you can use that to tell you which one needs to be retaught. So it'll show the point right here. Point 3 is the worst of these 4 points. So you can go back to point 3 and reteach it. The error is a deviation from the center of the closest group of points. Caution that the 3 points could be off. You don't necessarily your bad point that is declaring could be the one that's actually on. So make sure when you go to reteach it that you go back and look at it and see if it's actually where you want it to be. Then you may want to check the other ones to see if they're off instead. Acceptable max error depends on the process. Some processes allow errors, as I say, the 3 millimeters or so that were taught in this previous example. It may be acceptable. If desired, correct position with max error. So you go back to that point that had the max error and reteach it. A max and a mean that are close, maybe that 2 points are off. So when you do your calibration, and you see those two values are very similar to each other, you may have to go back and check them all and make sure you don't have 2 points that are off your probe. Again, you're going to use shift plus move 2 to check the points. And do caution you that when you use a shift plus move 2, you also got to hold the dead man, obviously, but I would move it up away from your probe first and then do the move 2 and let it come down to it. Because what can happen is the robot can swing through your probe and damage your probe. And then everything's off because your probe's no longer straight up and down or in the point or location that it was. All right, to correct in the 4-point method, you correct the approach point that is most off. Select the point on the screen and dead man plus shift to move 2, and then jog it to correct it, and shift plus record again. If there's no decrease in the error, it may mean that your overall mastering your robot is off. You might try a couple times to make sure that you're not seeing it decrease. If you see quite a bit of offset error, and once you've done it a few times, then you may want to go back and remaster your robot. if the max error switch it to another switches to another point, then that other point may need to be recalibrated too. So you may want to check it. All right. So again, to test this one, you're going to jog it with the yaw, pitch, and roll, and you should see similar results to the 3-point method. 6-point methods. Again, like with this welder torch, you don't want to take and just translate your orientation down to the tip of the welder torch. You want to realign your orientation to match your welder torch. So that's what the 6-point method allows you to do, along with the direct entry. So in the 6-point method, again, to access it, you'll go through the same steps: the menu, setup, frames, other, tool frame, method, and 6-point. You'll use comment to rename it to match whatever your process is again. And then the first 3 points record the same as the 3-point or the 4-point method. The orient origin point, which is this point right here, orient origin point. You'll want to line up your tool. In this example, we have an off-angle tool, kind of similar to a welder. You line up your tool to where your Z-axis is lined up with your frame, or your world frame Z-axis, parallel to your world frame Z-axis. And with the world Z pointing in the negative Z direction. So you're going to have your tool pointing down in the negative Z direction. You're going to, after you program your origin, you can program your X and Z point, or maybe X and Y, depending on which method you selected. You're going to want to move it at least 250 millimeters. So you move the robot in what you want your X direction to be, and then you'll move it or save that point with the shift plus record. And then you're going to move in the Z direction. If you move it in the positive direction as shown in this picture, you'll see that your Z is pointing into the tool. Negative, if you move it down, then the Z would be pointing out of the tool. All right, direct entry method. In this case, if you know your offset, like a straight probe or something, sometimes you can actually get your CAD data from CAD program and enter it directly from that. Or you can measure it directly. You can enter it into your X, Y, and Z, yaw, pitch, and roll here in the direct entry method. There are TCP correction devices out there. Obviously, the Leone is a very good TCP correction device that can actually set a TCP and make corrections to it just by rotating it or moving the probe around within that square orifice and probing it or going up and down in it and making circles. You'll determine where that point's at in space. There's also an IR vision correction method and a torch mate correction method. Both those are typically used with torches. In fact, they call that IR vision torch mate. The one in the top right corner, that one you can come down on top of the torch mate to tell the displacement Z, and then move it over to the side in that notch in the X and Y direction to get your X and Y offset. The Leone can be used with other than torches. It can be used with any kind of TCP that creates a probe type device at the end. But the other two are typically used with torch applications, welding applications. All right, so we talked about user frames a little bit. We're getting ready to start calibrating user frames. So you got their reference for all positional data, as I told you earlier. You translate the part to the robot. They're used, you can use them to repeat your program based on a new user frame, and you help match a linear move to a part's angle, right? Or basically match up your parts to your robot, to your frame. To get in the user frame, again, you go in the menu, setup, and then frames, and then other, and then user frame. Okay, so there are Again, they're default to 9 user frames. Unused ones will look just like this. They'll have all zeros, X, Y, and Z location. And they'll say U frame 1 or 2 or 3, whatever. U frame and a number for the unused. The hit method and 3-point. Once you've selected the user frame, you're going to hit enter or detail to get into it. And you'll select method and 3-point to select 3-point method. There is a 3-point, 4-point, a direct entry when you're doing user frame calibration. The 3-point method is very similar to the 3-point method in tool frame, where you have just 3 points to teach. You have a comment to rename, to tell it what you're using that tool frame or user frame for. And you'll use the Shift plus record to record the point. You only need to teach it the X and Y direction. You don't need to teach it Z. So you have an origin point and an X and Y point. Similar to what I'm doing here. You'll pick your origin point first, right? Where you want your frame to start, your 0, 0 location of your frame. Then you move your robot in the X direction, usually about 250 millimeters in the X direction. Then you can move the robot in the Y direction. You do not have to go back to the Y direction or the origin point before you go to the Y direction. You can just go straight out. It's just looking for an offset direction from that axis that you created for the X axis. And then after you've created all 3 points, it'll declare the frame. Your frame location shown and a plane that goes with that frame shown in RoboGuide. All right. Once you've set them, you'll see your X, Y, and Z and yaw, pitch, and roll for your frame that you created. You usually want to create your frame so that your X and Y locations that you pick will make your Z axis pointing up away from your table or whatever your surface is that you're creating your user frame on. Okay. The next method is a 4-point method, and that's typically used for a remote tool center point. So you have a additional system origin added for your 4th point. That system origin becomes your remote tool center point object. So what is basically the reasoning behind that is because you can want your 0, 0 point to be up here at your probe, but you have no X and Y plane here to reference to create your 3-point method. So instead of to orient your X and Y directions with some other object, you can orient with this table, for example, and then just translate the whole thing up to this point at this probe, making that your 0, 0 by using your system origin here. So you use the 3-point method basically to create this frame around the edge of the table. And the 4th point is a system origin point. This, again, the same entry method to get into it. Menu, set up other user frame method and 4-point. You set your first 3 points the same as you do in 3-point method. And then you set your system origin just touching pointer. Here's an example showing it being done. Again, orient point, then the X point here. Again, you can move in just offset off your Y. You get your Y point and then touch down on a probe to get the system origin point. And it declares a frame like that, where you got here's your frame, and this is the plane associated with the frame. Again, it's got the direct entry method in the user frame calibration. Similar to the tool calibration, if you know by CAD data or measurements where your user frame's at in relation to the world frame, you can just plug them in by going to direct entry method and plug in X, Y, Z, yaw, pitch, and roll. Testing a user frame, same basically as a tool frame, only you only want to do linear jogs to test this one, not rotary jog. You don't need to check orientation. So you're going to hold down the Shift plus the coordinate button, and it'll allow you to see the tool frame jog menu again. And you can change to the user frame that you calibrated, and coordinate button by itself. You can change the user frame jog method here. Jog frames, like I said, they're similar to user frames, only they're not really used in a program. Or not, you can't really use them in a program. They're just meant to line up your jogging with your part on your referencing on the robot, the fixture or whatever. You can set them up with any orientation and location. To get to jog frames, again, you go menu, setup other than jog frame. Again, left out frames. Menu, setup frames other than jog frame. Okay. So there you go. You got 5 different jog frames again. This again, they're the same setup except they're not used by the program. So you just do, I think there's 3-point method, and I think that's the only 3-point direct entry, I believe, are the only 2 methods you can do for jog frame. I don't think I referenced that anywhere. Again, jog frame testing, just like user frame testing, you're going to jog it in the linear direction and make sure your X and Y axis match whatever it is you're trying to calibrate it to follow. And then you got to go into Shift plus coordinate again to select which jog frame you want to use and change your jog method with the coordinate button to jog frame. You can save off your user frames, jog frames, tool frames, all your frames. You save them under a couple different file names. One's the frame variable.vr, which saves the jog frame and comments, and systemframe.sv, which saves all your tool frames and user frames. The comments that are saved in the frame var.vr are all the comments for all types of frames. First thing you got to do is set your default device. So you go into the file menu, go menu, then file again, and then you click on the button down at the bottom corner. It says util, and then you'll set device. You'll get a selection of all these different devices to be able to use. If it's, for example, if you want to use a USB disk, you plug a USB disk into your robot. This is the one that's on the robot panel itself. This is the one that's on the teach pennant. And you set the device to that. You select 7 for USB disk for the one that's plugged into the controller. Okay. So once you've set your device, you'll go back to frames, to any frame menu, user frame, jog frame, tool frame, whichever you want to be in. And you'll hit the function button on your keypad. And then you'll hit the save under function 2. And that'll save off your frame var and system frame var and sysframe sv files. To recall them, you'll again set your device like shown earlier. You'll have to set the directory to VR by hitting the directory button, which F2. After you set the device, then you'll select the frame var variable, file name, excuse me, and hit load, and that'll load back up your frames. There's a pop-up that comes up, and you just want to hit yes to that pop-up. All right, so you use these frames within your program. You want to create some instructions that call the frames, right? So you can either select new instruction from here or new instruction from here, and then select the offset frames. And then to access the frames that you want to set to active frames, you use the uframe_num and utool_num for the user tool. To manipulate frames, you use the uframe with the square brackets, and the user tool with square brackets allows you to assign store or modify frames. When you enter the user frame num, it'll give you some options for how to call up which user frame. You can either use a constant, or you can use a register or argument value. The register allows you to manipulate in the program which user frame that you're going to call up with that command. Here's an example showing how to use them in the program. I have start out with calling the user frame number 2, then utool number 3, and then I call a point and space, and it runs to it based on these two user frame and user tool numbers. Then it store that user frame within PR4, and then I call up the next user frame 1, and run that point and space again, and it's going to run to a different point and space because you used a different user frame number. Then I manipulate the stored frame that I stored in 4 by adding PR6 and store it in PR5. Then I call it back up again by pulling PR5 into a new user frame. Then I set that to my new user frame. You could call the same linear move to the same point in space, and based on that user frame, it's going to move to a completely different location. All right, and that is it for my frames presentation. Thank you for watching.